Hello everyone. So today we'll learn about subprograms. We'll learn about the introduction of subprograms, types of subprograms, benefits, scope and lifetime of variables in subprograms, passing parameters, recursion. So let's get started. So here we'll learn about those things that I just mentioned, like general concepts, parameter passing, functions, subprograms as parameters. So these are the things. So like um, basically subprograms, also known as functions or procedures, are the building blocks of modular programming. So we'll learn about parameter passing, which is one of the key aspect of subprograms. Then functions, which are specific type of subprogram designed to return a single value or result. Then subprogram as parameters, like a more advanced use of subprograms involves passing them as parameters to other subprograms. So here we have the general concept of subprogram. So basically, subprogram initially developed as procedures and functions. Um, it like this is not only save time. So basically, um, if we began the subprogram as simple tools, this is to avoid repetitive code, and this is not only saved time and reduced errors, but also began to shape how programs, like how programmers approached complex problems. uh, so we break the subprograms break the problem into smaller tasks, like manageable units, and subprograms became pivotal in promoting code reuse. So let's talk about what a subprogram is at its core. Basically, it is essentially a named block of code with a well-defined boundary and its own local scope. This means it operates independently of the rest of the program, encapsulating specific functionality. For example, um, in a banking application, a subprogram might handle the calculation of interest for an account. The rest of the program doesn't need to know how this calculation is done, just that it can call the subprogram when needed. Now, semantically, subprograms represent more than just blocks of code. They embody the concept of process abstraction. This means we can treat complex operations as if they were simple, elementary operations. This abstraction allows us to call these operations without worrying about the details of how they are implemented. It simplifies both the understanding and the use of the code, enabling programmers to think at a higher level rather than getting bogged down in the minute of data handling and control flow. And process abstraction is a powerful tool allowing for clearer thinking and better design in programming. It helps in isolating functionality, which not only makes programs easier to understand and maintain, but also facilitates easier debugging and testing. Okay, now let's define what constitutes a subprogram more precisely. Like a subprogram is not just any block of code, as I said earlier. It's a meticulously defined unit that adheres to specific rules and structures, making it a cornerstone of modular programming. So, at its core, a subprogram is defined through lower level operations. This means it is built upon more fundamental actions or commands that the programming language provides. These operations might include basic arithmetic, logic operations, or even other subprogram calls. Now, each subprogram has a unique identifier or name. This name is used to invoke it from other parts of our program, much like labeling a box to know its contents without opening it. So, naming subprograms helps us to understand their functionality at a glance. Then, subprograms interact with the rest of your program through arguments and return values. Arguments are the data you pass into subprograms, and the results are what you get back after execution. This mechanism of parameter passing allows for dynamic execution, where the same subprogram can operate on different data sets. Next, we can say when a subprogram is called, the program flow of the program is suspended. Sorry, the normal flow of the program is suspended. Now the execution context shifts to the subprogram where it runs its encapsulated statements. Now after completing its tasks, control returns to the point of invocation, often with a result. And this is like putting a bookmark in your book, going to reference another book, and then returning to continue where you left off. So, understanding these attributes helps clarify how subprograms function as self contained units within larger programs, promoting efficiency and organization. And they allow complex software systems to be broken down into more manageable, understandable pieces, each with a clear purpose and scope. Okay, now the subprogram header, often called the heading, includes essential elements like the name of the subprogram, the parameter passing module modes, and the type of value it returns. If it's a function, this header essentially acts as the definition or the signature of the subprogram, outlining what it expects as input and what it will provide as output. Then the subprogram body. Following the header is the subprogram body, which contains a sequence of statements that define the actual operations the subprogram performs. This is where the logic of the subprogram is implemented, from simple calculations to complex algorithm procedures. So next we have procedures and functions, which can be seen as extensions to the programming language. A procedure extends the language by introducing a new type of statement which can perform a series of operations and then terminate without returning a value. On the other hand, a function introduces a new kind of operation that not only performs tasks but also returns a value. This distinction is crucial in how we structure and understand the flow of data and control within our programs. Okay, parameters. Moving deeper into the structure of subprograms, let's discuss one of their most crucial aspects, parameters. Parameters are fundamental to the functionality of subprograms, allowing them to operate on different data inputs and maintain generality. Now, Think of parameters as generalized entities or placeholders within subprograms. They are like dummy variables that represent potential values. For instance, in a function that calculates the area of a rectangle, the parameters might be represented as length and width. These parameters don't have set values until the function is called. So next, the role of parameters is to make subprograms flexible and reusable. Instead of hard coding specific values, parameters allow a subprogram to perform its task on a variety of inputs. This versatility is what makes subprograms incredibly powerful tools in programming. So, when we discuss parameter passing, we are talking about the method by which values are given to these dummy variables during the call to a subprogram. So, if we look at here, now in programming, how we pass parameters to subprograms can significantly affect both the behavior and efficiency of our code. Now let's explore the different modes of parameter passing and the restrictions that apply to each. So first of all, value. If we talk about value, in pass by value, the actual value of the argument is passed to the subprogram. Changes made to the parameter within the subprogram do not affect the original argument. This is safe but can be inefficient for large data structure. Okay, now address. So pass by address or pass by reference involves passing the address of the argument rather than its actual value. So this allows the subprogram to modify the original variable directly, which can be more efficient but riskier as changes affect the original value. Next, we can say value and address. Third one. So some languages allow a combination approach where the subprogram can choose to either directly manipulate the original data or use a local copy depending on the needs of the program, need of the function and the design of the program. So also, uh, what are the restrictions on the use of the argument? So we can say read only. So parameters marked as read only cannot be modified within the subprogram. They are used to provide data to the subprogram without any risk of altering the input. Then write only. So write only parameters can be modified within the subprogram, but their initial values are not accessible. This might be used in situations where only the output from the subprogram is required and the input is either generated within the subprogram or irrelevant. Now read or write. Parameters that are both readable and writable offer the most flexibility but require careful management to avoid unintended side effects that can complicate debugging and maintenance. Okay, now let's take a look at a model for understanding procedures in programming, the black box model. Um, so here, if you look at this, okay. Now this is a procedure in the simplest terms is like a black box in an engineering context. Like you input data, something happens inside you don't need to worry about, and then you get an output. So this abstraction helps in managing complexity by hiding the detailed operations inside the procedure and focusing only on the inputs and outputs. So um, there are generally three types of interactions this black box can have with data, like input only. output only, and both input and output. So each of these interactions represents a different use case in programming. Okay, now the first one, input only. Data is sent into the procedure and no data is directly modified or output by the procedure itself. The procedure performs operations based purely on the input provided. Second is output only. The procedure data so the procedure produces data or results without needing external inputs. This might involve returning a constant value or data generated within based on internal logic. Third, we have input and output. Data is sent into the procedure, which then modifies this data and sends it back out. This is common in procedures that update or process data like sorting a list or adjusting account balances. So this model is particularly useful for understanding how to structure data interactions in larger software systems. By categorizing procedures according to what they require and produce, you can better design and integrate them into your overall program architecture. Okay, now we'll see pass by value. This approach has significant implications for both program behavior and resource management. So, in pass by value, a copy of the actual parameters value is given to the subprogram. So this means that the subprogram operates on a local copy of the parameter rather than the original variable. Changes made within the subprogram do not affect the original variable outside it. Okay, so this mode this mode is implemented by copying the actual parameters value into the memory space allocated for the subprogram's local variables. The local copy is what the subprogram manipulates, ensuring that the original data remains unchanged regardless of what happens inside the subprogram. So here we have three examples. So pass by value is the default mechanism in several programming languages. For instance, ADA uses in parameters to signify the variable is passed by value. In Pascal, it utilizes value parameters to explicitly indicate that the data should be passed by value. In Algol 68 and C, all parameters are treated as pass by value unless specified otherwise, making it a cornerstone of procedural programming in these languages. So, while pass by value is straightforward and safe, it can be resource intensive, especially when dealing with large data structures such as arrays. So each time a subprogram is called, a new copy of the data is made, which can lead to increased memory usage and slower performance. Okay, now let's see pass by result. So this mode is used primarily when the intention is to return a value from the subprogram to the caller rather than consuming input data. So basically pass by result means that the subprogram does not use the initial value of the parameter. Instead, it only generates and assigns a result to it upon completion. This is primarily for out parameters in ADA, where the parameter is intended to be written to, not read from, within the subprogram. So how it works? Now in this mode, the address of the parameter is made available um, to the subprogram, but not its initial value. Um, Throughout the subprogram's execution, this parameter is treated as a local variable that can only be written to. It's a write-only access parameter, which makes it unique compared to more common methods like pass by value or pass by reference. So this method is useful when the result of the subprogram is the only relevant output and the input, if any, is irrelevant to the generation of that output. For example, in a procedure calculating the result of a complex equation, the out parameter will store the result without any need to interact with the original value of the past variable. So technically, since the original value of the parameter is not utilized, this can help avoid unnecessary data copying, which might optimize performance in scenarios where the input value is large or complex. However, it also requires careful handling to ensure that the intended data is correctly written back to the calling environment. Okay, now let's see the another parameter, which is pass by value result. Um, this method combines aspects of pass by value and pass by result, aiming to provide benefits of both under certain circumstances. So pass by value result is primarily used with in-out parameters in ADA. It allows a parameter to be used both for input to and output from a subprogram. So um, here's how it works. Like when the subprogram is called, the value of the parameter is first copied into a local variable within the subprogram. This local copy is used throughout the subprogram's execution, just like in pass by value. However, unlike pure pass by value, once the subprogram completes its execution, the final value of this local variable is copied back into the original parameter in the caller's context. This is where it resembles pass by result. Now, this method can be quite useful when you want the subprogram to work with a value and then return a result without affecting the original variable until the very end of the subprogram. It provides a level of safety against changes during the subprogram's execution, but ensures that the updates are still reflected in the original variable afterwards. So while this method combines safety and functionality, it can be resource intensive, similar to pass by value, especially when dealing with large data structures or objects. The double copying into the subprogram and back out to the original variable can impact performance. Okay, let's see an example here. So let's examine a code to better understand how pass by value result works in practice. So this example will illustrate the flow of data into and out of the procedure, highlighting the dual nature of this parameter passing method. So here, first of all, the procedure P is defined with a parameter X that uses the in-out modifier, indicating that X can both supply an initial value and receive a final value. Z is a local variable within the procedure that initially receives the value of X. This isolates X from changes until the procedure is ready to assign a final value back to it. Inside the procedure, Z is used for all computations and modifications. These separations ensures that the external variable X remains unchanged if the procedure encounters an error or needs to exit early. So, after all computations are complete, the result is assigned back to X from Z. This final step effectively makes the changes visible to the caller, ensuring that the updated data is returned. Now, this method can create complex behaviors, especially if X is involved in expressions or conditions before and after the call to P. Now, the sequence in which parameters are evaluated and assigned can significantly impact the programmer's behavior or the program's behavior, sometimes leading to unexpected results. Okay, now let's see the pass by reference, which is a common method of parameter passing that allows subprograms to modify the original argument passed to them directly. This approach is widely used because of its efficiency and simplicity. So, in pass by reference, um, instead of passing a copy of the variable's value, the subprogram receives the address or reference of the variable. This means that any changes made to the parameter within the subprogram affect the original variable. Now, how it's implemented? So, this method is implemented through indirect addressing. Which means the subprogram operates directly on the memory location of the variable because it uses the variable's address. No additional copying of the variable's data is necessary. So, like which saves both memory and processing time. So, we have two examples here, like in Pascal language, it uses the var keyword to specify that parameters should be passed by reference. This makes it clear in the function declaration that the original data can be modified. Then second one is Fortran. Like traditionally, all parameters in older versions of Fortran are passed by reference, simplifying the handling of large data structures like arrays and records. So, pass by reference is particularly useful for handling large data structures or when the subprogram needs to modify the input data directly. It is more memory efficient than pass by value as it avoids creating additional copies of data. However, it requires careful handling to avoid unintended side effects since the original data is directly modified. Okay, now let's examine a practical example of pass by reference. Here we have procedure P VARX, like some type. It declares a procedure P that takes a parameter X by reference using the VAR keyword in Pascal. Now, this means that X is not a copy, it's the original variable passed from the caller. Now, inside P, any modifications to X will affect the variable Z in Q since X and Z refer to the same memory location. For example, if X is assigned a new value, Z will hold this new value once P completes. Now in procedure Q, a variable Z is defined and initialized. When P is called with Z as an argument, P receives a reference to Z. Changes to X within P directly modify Z. Now after P is called, any changes made to Z inside P are preserved and will be visible in Q. This demonstrates how pass-by reference allows a subprogram to alter the state of variables defined in its caller's scope. Okay, now let's see another practical example for parameter passing. So here we have the variable j, which is set to 3 and a3 is set to 6. These values set the stage for our swap operations. So procedures like the swap procedure is designed to take two integers by reference, allowing it to swap their values. TMP is used as a temporary storage to facilitate the swap. Then the swap procedure is called with j and aj as arguments. Because both parameters are passed by reference, any changes to x and y inside swap affect j and aj directly. Now after the swap, j becomes 6 and a3 becomes 3. The array's third element and the variable j have effectively swapped their values. Now the write statement outputs the new values of j and a3, which will be 6 and 3 respectively, demonstrating a successful swap. Now in mode, we have in mode, out mode, in out mode, if you remember from our parameter modes. So on in mode, it will not allow the swap to modify j and a, as the parameters would be read only. And on out mode, that would be impractical here, as it does not allow reading of x and y, only writing to them. So on in out mode, this is the mode used in the example. So this is the mode, in out mode, that we used in this example, where it allows both read and write access to the parameters, and which is necessary for swapping their values. Okay, now let's see some critical aspects and distinctions of parameter passing methods, particularly focusing on the nonsense between pass by reference and pass by value result. So a significant challenge with pass by reference is aliasing, where two different parameter names refer to the same actual memory location. This can lead to unexpected behavior, especially if the subprogram modifies the data. For instance, if the same variable is passed as two different parameters to a subprogram, changes to one parameter will affect the other, potentially leading to bugs and hard to track errors. Second, we can say for pass by result, pass by value result, and pass by reference, it's crucial that the actual arguments must be variables. This is because these methods involve either direct modifications of the variable or a need to store the results back into the variable. Okay, now pass by reference and pass by value results serve different purposes and have distinct behaviors. So if you talk about the actual data is directly accessed and modified in pass by reference, with all changes reflected immediately in the calling environment. So This method is efficient for handling large data because it does not require copying data. Where on pass by value result initially acts like pass by value by copying the data into a local variable, and then behaves like pass by result by copying the modified data back into the original variable at the end of the subprogram. So this method is safer and in concurrent environments or where modifications need to be controlled by but is less efficient due to the double copying process. Okay, now let's see prologue now. So here prologue like um Prolog is distinct from other programming languages due to its logic programming paradigm. This difference fundamentally changes how data is handled within functions or predicates. Now, unlike imperative languages where you have addresses and values that can be manipulated directly, Prolog operates on a different principle. Um, In Prolog, there is no concept of variable addresses, and all variables are effectively immutable once they are bound to a value. There is also no direct assignment operation like in languages such as C or Java. So here is an example. So um, let's consider the append predicate in Prolog, which is used to concatenate two lists. Now, the parameters in append are typically classified not by in, out, or in out modes, but by how they are used in specific calls. For instance, we have the first one append A, B, result. So here this append has A and B as input lists and result as the output list, where the concatenate result is stored. Now second one we have append first second AB, reversely deducts possible values of first and second that could result in AB, making them effectively outputs in terms of logical deduction. So in Prolog, the role of parameters can change based on how um, predictable. A parameter can act as input, output, or both. So the typical classifications of parameter passing do not straightforwardly apply to Prolog. Instead, understanding the behavior of predicates in Prolog requires thinking about how terms unify during predicate resolution and how this unification affects the predicate's logic. Okay, now let's talk about functions. So functions are fundamental to enhancing the expressiveness and capability of any programming language. Now let's see function here. Now a function in programming is designed to perform a specific task and produce a single value, which is returned to the caller. This return value can be generated in several ways, such as through a direct return statement or by assigning a value to the function name in languages like Pascal. So, when functions are integrated into expressions, they effectively act as extensions of the language. For example, even if a programming language does not natively support certain operations, functions can be created to handle these operations. So This ability to define new functions allows programmers to add features to the language that fit their specific needs. So here is the example. Like consider a function x expxy designed to calculate x to the power y. Now the exponentiation of x by y, which might not be natively supported in some language, but here's how it could be used in an expression. So z colon equal to 2.0 multiplication exponential expan. So in this expression, expan computes a to the power n, and the result is then multiplied by 2.0. This is not only makes the codes more readable but also modular and reusable. So by defining functions like exp, programmers can introduce complex operations into their code in a manner that is both natural to write and easy to understand. So functions can be used in various expressions, making them versatile tools in both simple and complex programming tasks. So there are some side effects also. So side effects occur when a function modifies some state outside its local environment or has an observable interaction with the outside world besides returning a value. This could include altering the value of a passed parameter, changing a global variable, or performing I/O operation. So ideally, a function should be pure, meaning it should not have any side effects. Um, so a pure function's return value should only depend on its input parameters, and it should not alter the system of the alter the state of the system. So this ensures that functions are mathematical in their operation, making them easier to reason about, test and reuse. However, side effects are sometimes necessary. So especially in procedural programming, um, where changes to the system state are required. In such cases, it's recommended to use procedures instead of functions. Procedures can be designed specifically to handle tasks that involve changing states or performing actions, while functions can remain pure and dedicated to computing values. So a related design issue is orthogonality in the types of objects returned by functions. Orthogonality in this context refers to the principle that system components should behave independently of each other. By restricting the types of objects a function can return, we can reduce complexity and enhance modularity, ensuring that functions remain manageable and predictable. So if we talk about a practical example, consider a function that retrieves user data from a database. To maintain purity, the function should return the data without directly modifying the database or any global state. Any necessary state changes should be handled separately through specific procedures designed for that purpose. Okay, subprograms as parameters. So, um, this approach allows algorithms to be more flexible and powerful by embedding one algorithm within another. So, the idea here is simple yet profound. A subprogram, which can be a function or a procedure, accepts another subprogram as a parameter. This enables the creation of higher order functions where functions can operate on or return other functions. This capability greatly enhances the modularity and reusability of code. Now, Scheme, a dialect of Lisp, is particularly well suited for this pattern due to its support for first class functions. In Scheme, uh, functions are treated like any other data type, meaning they can be passed as arguments returned from functions as and stored in data structures. Let's consider a practical example here, numerical integration. So, numerical integration involves calculating the area under a curve represented by a mathematical function. By passing the function that describes the curve as a parameter to an integration subprogram, we can calculate the area under any curve defined by any function, not just a pre-specified one. So, um, here we have the pseudocode. If we talk about this subprogram as a parameter, so if you take a look at this example, which will help us understand how passing functions as parameters can be utilized in imperative programming languages. So here the function f argument real is a parameter of the definite integral function. It allows any function of type real to be passed in, so making this integral function generic and applicable to any suitable mathematical function. So then the method used here is a simple form of the trapezoidal rule. So where the area under the curve is approximated by summing up the areas of trapezoids under successive intervals. The function begins at low, calculates the function value there, and iteratively adds the values obtained by applying f at intervals defined by delta. And now each new value of x within the loop is calculated by adding delta to the previous x. The sum accumulates the values of 2.0 multiplied by fx across the interval, so doubling each midpoint's contribution except for the first and last point. So the final value of the integral is computed using the average height of the trapezoids times the total width. So then we have 0.5 multiplied by delta multiplied by sum, so to estimate the area under the curve. So this is our final value. Okay, now let's explore another practical application of the concepts we have discussed, specifically how to use subprograms as parameters by integrating a simple function over an interval. Now this example uses a function for squaring a number and passes it to our definite integral function. So first of all, here we have sq. Sq is a simple function that takes a real number a and returns its square, a multiplied by a. This function conforms to the type expected by definite integral. It takes a real number and returns a real number. Then we pass the sq function as a parameter to definite integral. This demonstrates how functions can be passed as arguments, allowing definite integral to compute the area under the curve y equal to x to the power 2 from 0 to 9. Then the integral is calculated, which is approximately 243 represents the area under the curve of the function y over the specified range. This value is significant in demonstrating both the correctness of our integration function and the versatility provided by higher order functions in handling various mathematical problems dynamically. So, using subprograms as parameters not only simplifies the implementation of complex algorithms but also enhances the modularity and expressiveness of our code. Would you so here the pattern this pattern is particularly common in functional programming but is also very useful in procedural languages that support passing functions as parameter like Pascal. So that's all for today's lecture. If you have any question or concern, let me know. Thank you.